You come in from the waiting room, slowly appearing in front of me. It's quite eerie, really. It's very strange. Welcome everybody to Cafe Sci. This is actually Cyber Cafe Sci. Okay, I give people time to come in here. And we've got some people watching on Twitter and Facebook live as well. Okay, to those people who are looking on the live streaming platforms and not on the Zoom, you can ask questions and intervene, but I may miss them. James might be monitoring those streams and will let me know the questions that you have, and you'll be a few minutes behind the rest of us. To those of you who are on Zoom, welcome. You're participating live in a Cyber Cafe Sci. Just a few things. We welcome questions as we go through. And if you look somewhere on your screen, on mine, because I'm on a PC, it's at the bottom of my screen, is a Q&A. And the Q&A allows you to pose a question. And what will happen is, mostly, I will sort of look at those, and then at an appropriate moment, I will interrupt Sapphire and put the question to her so that she can answer it. And if you're willing, and it's a question that requires a bit of dialogue, I can put you on so you can speak and be seen and have a conversation about that, but that's entirely up to you. Okay, just a little bit of background about the Cafe Sci. So Cafe Sci is a global movement for informal science. It's really more about who is interesting and interested. And ours was in Woking. We've been going, I think now, for nearly 6 years. But of course, we had to go online during the pandemic, and we've taken the opportunity to run weekly so far. And also we can reach out to a wider array of speakers and a wider audience than just those people in Woking. So that's been very nice indeed. It means we get a much more eclectic mix of people, so I don't recognize all of the names, and welcome to those of you who I don't know so far. I hope I get to know you in time. This week we've got Sapphire Lally, and Sapphire is a late stage PhD student in the Quantum Biology Institute, which is kind of cool. You know, quantum biology, so quantum physics interacts with biology and causes things like, I think, robins being able to find out where they are and which way up they are and things like that. It's absolutely fascinating. And we had Sapphire talk at our live Cafe Sci in Woking, and you're in for a treat. Well, I hope you are. You're in for a treat, because Sapphire is one of those quantum physicists who can explain the extraordinarily complicated in small sentences so that you follow it all the way through. And whenever I hear someone like that speak, I'm absolutely in awe, because I'm like, oh my God, I can follow every part of this. The only problem is at the end of it, I can't remember any of it. But as you go through, really, you feel like you're understanding it, and it's really cool. Sapphire is actually a quantum physicist, although she works with biologists, and she's particularly interested in some of the more obscure aspects of quantum physics, and I'll pass over to her in a moment. But she's chosen to speak about David and the Goliath, and that's the connection between quantum particles, some of the smallest, tiniest things in the world, and black holes. So are you ready, Sapphire?
Yes, I am ready. Thank you very much.
Okay, I'll pass over to you.
Thank you. I'm just going to try and figure out if I can share my screen. So if you bear with me for a couple of moments, and there should be some pictures coming up. Okay, so thank you very much, Chris, for that introduction. And thank you to everyone who's come along this evening. As Chris mentioned, I will be talking about what I've decided to call David and the Goliath, which is the relationship between quantum mechanics and black holes, these really giant beasts that roam the universe. I am a quantum physicist, so it's been a little bit out of my comfort depth talking about black holes, but it's been really nice to step away from these tiny things and start looking at something a bit bigger for a change. Chris mentioned that I work in the Quantum Biology Doctoral Training Centre, which is down at the University of Surrey, headed up by Professors Jim Al-Khalili and John J. McFadden. And what we focus on is trying to find signatures in biological systems of quantum physics. So for example, Chris mentioned that robins are able to use quantum physics to navigate. That's probably due to a quantum effect in a particular protein they carry that allows them to sense magnetic field lines. We're also wondering about the possible effects of quantum mechanics in DNA mutations, in enzymes, and in DNA repair mechanisms. So there's a very wide field of interest. Just before I begin, I want to give a brief, not an apology necessarily, but a sort of notice. I am very unused to talking where I can't see the audience, and this feels very odd for me. If any of you have given presentations over Zoom, you probably know what I'm talking about. So if I come across a little stilted, it's because I've just got distracted by the lack of visible audience. So I want to remind you all of the story of David and the Goliath. I think it'll be familiar to at least some of you, and maybe even all of you who've joined us. So this is a story from the Bible, and it involves the story of a battle between the army of Israel and the army of the Philistines. Israel sent out as their champion a young boy called David, and they sent him out to fight against the mighty Goliath, who is rumored to be somewhere between 6'9" and 9'9". When David was offered armor and shields and weapons by the king, he declined and said, "No, I will fight with what I'm used to." And he took only his sling and some stones from the riverbed. When he walked out into the battle, everyone laughed, and the Philistine Goliath said, "There's no way that this boy will beat me." At which point David promptly put a stone through his forehead with a sling and felled him in one blow. This has nothing really to do with black holes, but I think it's a nice metaphor for what we're about to be talking about. And as we go on, you may come to agree with me. So moving on to the talk proper, I want to start with a slightly unusual reminder. The way we have evolved to see the world in terms of 3 dimensions of space and 1 fixed dimension of time is nothing more than a convenient approximation. We've evolved to see the world in terms of other beings who act much like us, and plants and the sky and everything that's within our environment. But that's no more of the real universe than the visible light we can see is all of the electromagnetic spectrum. We have absolutely no idea what X-rays would look like to a being who was able to perceive X-rays. And we have similarly absolutely no idea what something in 4 dimensions would look like. But that doesn't mean it's any less real than an X-ray is, just because we can't interact with it in a way we used to. Some of the concepts we'll be talking about tonight are completely counterintuitive to the senses we've evolved for living in a 3-dimensional classical world. And as such, they'll be really hard to wrap your head around. But that's okay, it's natural and it's normal. So if you're getting confused at any point, feel free to put a question in the Q&A, and I'll try and stop, rewind, and make everything as clear as possible. So, in modern physics, we have divided up the universe into 2 main theories. We have quantum theory, which gets to play around with electromagnetism and the weak interaction and the strong interaction. And that primarily deals with really small stuff. It tells us how atoms work, how electric currents work, how nuclei behave when they interact with each other. And it's remarkably powerful. Even though it deals with really small stuff, all of the forces are very strong, and it ends up describing how stars burn, which is probably one of the most important mechanisms in the universe. On the other hand, we have gravitation, and that's described by general relativity. It might seem unfair that general relativity only gets 1 force to play around with, whereas quantum theory gets 3, but gravitation ends up dominating the large-scale structure of the universe. So while quantum mechanical effects might power the core of stars, they're brought together by gravity, and then gravity goes on to form solar systems, galactic clusters, and galactic superclusters. Relativity has a couple of key ingredients, which we often call Einstein's postulates. Number 1 says that essentially there are no privileged observers. We might observe things differently to each other based on things like relative velocity or proximity to massive objects, but neither one of our observations or our experiences of the universe is more true than anyone else's. Relativity should explain how, in different circumstances, either observation can be seen. It's like a train traveler who sits on a train reading a newspaper and says this newspaper isn't moving. But someone standing on the platform who sees the traveler go in a train past the platform says, wow, that newspaper is moving at great speed. It would be a slightly odd thing to say if you're standing on a platform, but the point remains that we are quite happy with the idea of different kinds of observation based on different circumstances. Relativity is kind of like an extension of that, but in more fantastical terms. It might tell us about 2 apparently conflicting outcomes, But in the framework, we can see that both of them can be simultaneously true. The second postulate concerns the speed of light, and it says that
Can I just interrupt you, Sapphire?
Yes.
Yes, just to point out that the bottle is not as huge as it appears. It's a matter of perspective. It's a very small bottle she's drinking from.
Hold it by my head. It's an entirely
Okay, carry on.
So the second point concerns the speed of light, more specifically the fact that nothing should exceed the speed of light in a vacuum, which is about 300,000 kilometers per second. The speed of light is sometimes called the speed of causality. Nothing can get anywhere before light does, and if it were to somehow travel faster in light, it would be traveling backwards in time. One more final important takeaway from relativity. We can no longer have space and time operating as independent concepts. Instead, we have space-time, which is a kind of malleable or flexible blend of the two, and I think I have a picture of it there. Space-time is deformed by the presence of mass or the presence of energy, and these are gravitational effects. It can also have, and it can be warped to different extents. So in the picture here, we have a crude model of space-time being warped by something as heavy as the sun, something as heavy as a neutron star, and finally something as heavy as a black hole. And you can see in each of them that the well gets deeper and deeper. The picture of the black hole is actually inaccurate. It should be a well that goes on forever, and we'll come to talk about that a bit more. Space-time can have positive or negative curvature, but it can also be flat. As far as we know, we live in a universe that's very, very nearly flat, to within a couple of thousandths of a percent. You may have heard it described in science videos or articles as asymptotically flat. This just refers to the fact that there are fluctuations caused by gravitational effects, but in the grand scheme of things, it's pretty much flat. One of general relativity's most dramatic outcomes is the existence of black holes, or the prediction of the existence of black holes. Areas of space-time that have been so dramatically warped by mass that nothing can escape. It's like traveling down a river towards a waterfall. As you get closer to the edge, you have to paddle harder and harder and move faster to avoid getting swept away. And it's at a certain point, the river gets so strong that you can no longer paddle away from the edge of the waterfall, you get pulled in. A black hole is similar, but it's such an incredibly dense region of space-time that it gets to a point where you'd have to travel as fast as light to be able to get away from it. And as we know from the postulates of relativity, nothing can travel faster than the speed of light, but nothing that has mass can even reach the speed of light. So there's a certain point, and once you cross that, there's no getting away from the black hole. This is called the event horizon. There are two important parts of a black hole. Firstly, we have the event horizon, which is this point of no return that I've just described. When you see a black hole referred to by size, this is normally in reference to the event horizon, and it refers to the diameter of the event horizon or the space contained within it. Because the second important part of the black hole is very badly misunderstood. The singularity.
We've got two questions, if you don't mind.
Go ahead.
So first of all, why can nothing travel faster than the speed of light?
Okay, so this is a postulate, which means we didn't derive it. We decided to act as if it's true and then see what happens. The reason we decided to act as if it was true is because we'd been trying to measure it for a really, really long time and never seeing a variation. We tried measuring it at different points in the Earth's orbit when we were moving in different directions. And with any normal acting wave, you would see a difference in direction when the Earth was traveling that way around the sun and when it was traveling that way around the sun, because we'd be going either with it or against it. But we didn't see these changes in speed at all. So given that we couldn't find any evidence that the speed of light could ever be measured differently, Einstein decided to say, well, let's see what happens if we fix the speed of light as constant for every observer. And he ended up deriving these theories of relativity, special relativity, and general relativity. And the predictions we get from those are completely true, insofar as we've been able to test every prediction made with unbelievable accuracy. So given that we can say what happens if the speed of light is constant, and then get all these true predictions, we're pretty sure that the speed of light must be constant because reality matches up with the logical deductions of that. Of course, that doesn't mean this, like, as with all science, there may be an improved model somewhere down the line in the future that says, well, actually, certain things can be shifted, but we haven't got to that point yet. And we're pretty confident that we can say it's true because we haven't found anything that suggests it's false. That's not always necessarily the most satisfying answer, but I think it's probably a good one.
Good enough. And second question, Einstein said energy and mass were equivalent. So if something has energy, does it not have mass? And so if something's traveling at the speed of light, it must have energy. Doesn't it therefore have mass? But you said that nothing with mass could travel at light speed.
I understand the question. The equivalence actually goes the other way around. So it's not that energy is mass, it's that mass is energy, which may sound like the same, but it's a slightly different statement. So for example, a photon can have energy without having mass. Anything that has a mass has kinetic energy, but it also has energy that comes from the mass. So mass is just one thing that contributes to energy rather than being all of energy. Does that answer your question?
I think so. If not, the person will come back to me. Thank you.
I just wanted to touch on one more thing about the question about the speed of light, if that's okay. There's a slightly more complex point involving time dilation. Time dilation is the feature of time slowing down depending on how fast you're traveling in space. So the faster you're traveling, the more time slows down. When you get to the speed of light, time completely stops. So a photon, if it had a consciousness, wouldn't experience the passing of time. Everything that happened in that photon's lifespan would happen to it at the same time. So we can't really extrapolate further than the speed of light in that series of events. We don't know what it would look like to have time that goes slower than not moving, other than moving backwards in time. And we're pretty confident we don't want that to happen because that would play all kinds of havoc with causality. And so far as we can tell, causality is pretty well, causality exists in the universe. So there's a couple of sort of, in theory, reasons for the speed of light being constant as well. Okay, getting back onto black holes. I mentioned that there are two important points. First, we have the event horizon, which is this point at which once you've crossed it, you can no longer cross back out of it. Secondly, we have the singularity, which is this infinite point at the center of the black hole. It's a point of infinite density, and we don't have the physics to talk about what that looks like at all. We don't know if it goes into a white hole and comes out in a new universe. We don't know if it just somehow breaks the universe completely. We don't have the theory to talk about it. So for the time being, I won't. Most of this discussion will be with reference to the event horizon. I've rushed through all of that really quickly. In general, relativity could be its own talk. And I would love to take far more than half an hour just to talk about this, but we've got a lot of material to get through, so I wanted to just rush past that. Okay, so black holes, that's all done and dusted, right? We've got an incredibly dense mass that warps space-time. It forms a black hole and nothing can escape from it. Those are all gravitational effects, so these are all just things in general relativity. But of course, when we start looking deeper, things get more complicated. They usually do. Let's start out by thinking about something called information. Lots of physicists think information is more fundamental than other things like mass and charge and so on. In fact, mass is information. It's like a little tag attached to a particle which tells you the value of a specific property. Other properties can have information tags as well, like spin and charge and position. If the universe were a giant computer, and let's face it, it might be a giant computer, The information would be the ones and the zeros that encode everything going on. So what happens to all the information that gets chucked across the event horizon of a black hole? Well, it's lost to the rest of the universe because nothing can cross the event horizon to have a look and then come back. And sure, you could yourself cross the event horizon to have a look and find out what happens, but you wouldn't be much use to the scientific community because we wouldn't be able to email you to get your results or anything. But the thing about hidden information is that that's what entropy is. Entropy pretty much refers to the amount of different ways you can reorder the components of something and still have it look the same. So a sandy beach has really high entropy because there are a lot of ways you can reorder the grains of sand on a beach and still just get a beach. But I have comparatively low entropy because if you started moving my cells around, eventually you'd get to something that really made a difference and I'd start to look pretty odd quite soon. When you think about it like this, a black hole has lots of entropy because it doesn't matter how you order the stuff or the information on the inside, it still just looks like a black hole.
And it's time for me to ask a question. So from Isaiah, going back a bit, what is a white hole?
Okay, a white hole is kind of like the opposite of a black hole. In physics, everything is time reversible, which means that if you can have a solution going in one direction, you really ought to be able to have it going in the other direction. And the time reverse of a black hole is called a white hole. And it's something that once you've got out of it, you can't go back into it. We're not sure if these exist. We've never seen the signs of one in our own universe, but the mathematics does allow them to exist.
Thank you. And second question from Sarah, what is causality?
Okay, so causality is saying that if A comes before B, then B cannot influence A. It's basically saying that there is a chain of events that happen in a certain order. So A comes before B comes before C, and C can't come before A. It's a way of saying that you can't travel back in time, essentially.
Okay, thank you.
Okay. So we've just realized that black holes have entropy. The man who first calculated this result was called Jacob Bekenstein, and he got a fairly surprising result. It turns out that the entropy of a black hole isn't proportional to the volume, which is what we see in gases and solids and many other objects. And you'd kind of expect the entropy to be proportional to a volume because it's telling you about how much stuff there is, and stuff there is pretty much what volume is. But the entropy of a black hole actually ends up being proportional to its surface area. So the surface area is all the area on the outside. So it's like a shell surrounding the black hole at the event horizon. Although initially surprising, this does kind of make sense, but we need to go back to general relativity to think about why. Let's think about what happens when something crosses the event horizon. Let's say maybe one of you crosses the event horizon and you have a friend who's in a spaceship above the event horizon watching you approach certain doom. The person who crosses the event horizon doesn't notice anything weird happening necessarily, but the person watching them sees them get slowed down. As they approach the event horizon, light takes longer to get to you because it has to travel further out of the well of the black hole. If you look at the picture on the PowerPoint presentation, you have to imagine the light traveling all the way up out of that well to get to you in the flat area of space-time. So watching someone fall into a black hole is like watching someone slow down. And eventually there's a last bit of light that can get to you because light travels at the speed of light. So just before the event horizon, it can still escape. But at the event horizon and beneath, it's gone forever. What that means is you'll see the person who crossed the event horizon frozen on the surface because that's where the last light that can get to you came from. We'll probably come back to this point, so it's worth remembering it. Of course, when we talk about entropy, we also have to talk about temperature. This is the law of thermodynamics. Anything that has entropy also has a temperature. So if a black hole has an entropy, it must have a temperature. But things that have a temperature tend to radiate. So if a black hole has entropy, it must radiate. Stephen Hawking wasn't very happy about this because of the whole nothing that crosses the event horizon can come back out thing. So he set out to prove it wrong and promptly accidentally proved it right. Black holes do radiate, and the radiation is called Hawking radiation, obviously in honor of Stephen Hawking. Hawking radiation is one of those things where you might hear a couple of different arguments explaining it, and that's because matching mathematics up to actual physical things can occasionally be quite difficult. We're trying to put weird effects from quantum field theory into brains that evolved to think about mammals and plants and not much else. So it can be difficult to think about these things in terms that make sense to us. But all the possible explanations involve effects at the event horizon. I'll give you Hawking's original argument. Let's say a vacuum state approaches the black hole. A vacuum state is composed of many different wavelengths added together. So they all kind of cancel out. So many different wavelengths added together, and they're at different phases, which means that one of the waves might be like this, while one of the waves is like this. And when you add them together, they cancel out to flat. Ah, I have a picture of entropy there. Okay. The gravitational differential as you approach the event horizon means that these modes at different wavelengths get scattered different amounts based on their wavelength, just like light being split through a prism. So some of the modes are pushed across the event horizon into the black hole, and some of them are pushed outside where they can escape to infinity. But the thing is, the escaping modes now aren't a vacuum state anymore because they've lost some information, so they've lost some modes. It's kind of like taking red light out of white light. You'd now get something that was almost white light, but not quite. So this escaping vacuum state coming out of the black hole, which now isn't a vacuum state, looks like it has particles in it, because some things that were cancelled out before by things in opposite phase are now no longer cancelled out, so you have an actual particle there. To a distant observer, the black hole looks like it's radiating particles, and according to Hawking's calculations, will eventually radiate away completely. You can use a neat bit of mathematics that shows that the wavelength of Hawking radiation is about the same as the radius of the black hole. So to a distant observer, they can't pinpoint the source of the radiation as coming from a particular point on the surface of the black hole. It's just coming generally from that area, and you can't resolve it any clearer than that.
And we have a George question, which is detailed and clever. I'll read it to you. Given that a photon does not experience time, when it is emitted from an electron, does it already know what it is going to be absorbed by? And supplementary, what happens to a photon that heads off in a direction where there is nothing for it to encounter?
Okay.
That's a philosophical George question. Well done, George.
Very good questions. It depends what you mean by know. Can a photon know anything? I would argue that knowledge is a difficult concept to translate to photons, but I take your point, and the answer is yes. A photon experiences emission and absorption at the same instant. And if a photon just heads out in a direction where it doesn't hit anything, then it just carries on going. If you've heard of cosmic microwave background radiation, that's basically a whole bunch of photons left over from the Big Bang that haven't yet been absorbed by anything. And we're currently busy absorbing them in our telescopes and whatnot, but there's a lot of them out there just kind of hanging around, and they've slowed down. So they're now at about 2.3 degrees Kelvin, I think, which is very, very low energy. Okay. The description of Hawking radiation is a little bit difficult to imagine, so please feel free to put a question in the Q&A. But I'd encourage you to think about it using this Pink Floyd picture. But the incoming white light is like the vacuum state. The prism is like the event horizon of the black hole, which scatters the wavelengths of the vacuum state. And then some of them get missing. So even if you recombined all those wavelengths, you wouldn't get white light anymore. You get something different. The same thing happens, but it's a vacuum state that suddenly no longer is a vacuum state. It's something that looks like it has particles in it. So now we have all the ingredients to define a problem. The black hole information paradox, specifically. If the black hole radiates away, what happens to all the information we've chucked in over the horizon? Specifically, the quantum information. Quantum wave functions are forwards and backwards deterministic, which means that the wave function at any future or past time can be uniquely determined by the present time, if we get rid of things like measurements which collapse the wave function. This means that quantum information is conserved. We're not allowed to do things like chuck it into a black hole and then let the black hole radiate away. We need to keep track of the information. So we have a conflict between quantum mechanics and general relativity. Quantum mechanics says, hands off my information, and would really rather the black hole didn't radiate away and could just function as a storage space for information. But general relativity says, sorry, and radiates away anyway. So the central question in the black hole information paradox is, what happens to the information? We can actually reframe this as a question that's a little bit easier to tackle, which is, does the Hawking radiation contain the missing quantum information? I see there might be another question coming up. Chris, do you want to interject?
I didn't see that one yet.
Oh, okay. I thought another would go up, but I might be working.
Oh, no, there is. You're right. Oh, the speaker's ahead of me. I'm supposed to monitor the questions and feed them to you. Brilliant. Yes, so a George supplementary. Am I correct in thinking that a black hole can only evaporate completely once it is no longer accreting any new matter?
Yeah, pretty much. So the question we're talking about is sort of late stage universe. What happens close to the heat death of the universe when all matter is very, very spread out and much of it has fallen away into black holes? Accretion of matter is faster than Hawking radiation. So if you're making up for the information you're losing, the matter you're losing and then some, then you don't have to worry about the black hole radiating away completely. The information question still exists though, I think, even before the black hole's completely radiated. It's just the complete radiation puts it into a very sharp focus. So
thank you.
Originally, Hawking said, absolutely not. The Hawking radiation can't carry information. No information can leak out from a black hole. That's the whole point. You'd have to significantly violate relativity. Information that has passed the event horizon can't be found outside the event horizon. Otherwise, what's the point in having a black hole? Now, I think we can all agree that Stephen Hawking is pretty great, but he doesn't have a great track record of making predictions in this particular area. He was wrong about black holes radiating, and it turns out he's wrong about this as well. Let's take a closer look at what we mean by the process of something falling into a black hole. Of course, what we mean by this is something crossing the event horizon, because we don't know what the singularity will look like, and we tend to use black hole to mean the area inside the event horizon. The thing that crosses the event horizon will also gravitationally affect the curvature of space-time, and therefore it will have a very small effect on the black hole. This is kind of like planetary orbits. We tend to think of Jupiter and all the other planets, but Jupiter's in this picture, as orbiting the sun. But because Jupiter also has a mass, it has a gravitational pull. And actually the sun and Jupiter tend to orbit each other with the barycenter, which is the center of the orbit, slightly outside the sun. So the sun wobbles a little bit, whereas Jupiter makes a big orbit. The same kind of thing happens when something crosses the event horizon. Mostly the little thing that crosses the event horizon is what experiences the big change, but the black hole will also have a little bit of a wibble. So at the point where an object crosses the event horizon, there'll be a tiny distortion on the surface of the event horizon, like the sun wibbling around the barycenter. The event horizon's no longer a perfect spherical shell, it's got a little bump on it. Now, if you remember the discussion of Hawking radiation, you'll remember that the radiation is scattered around the event horizon and has a wavelength about the same size as the black hole. So it can't help but interact with that little bump on the event horizon, regardless of when that occurs. And it can pick up the information that way. The information is encoded in this little fluctuation, and then the Hawking radiation interacts with that, and bingo, off it goes, carrying the information away into the universe before the information has fallen into the black hole. Now, if you think back to Bekenstein's calculation of entropy being proportional to the surface area, this now makes even more sense than it did before. The information about the interior of a black hole, the things that have fallen into it, live on the surface in the form of these fluctuations on the event horizon. It even makes sense when you think about the observer who saw her friend fall into a black hole. She saw her friend slowly moving in and eventually getting stuck on the black hole's surface. The information about her friend lives on the black hole surface. We call this a hologram because we've taken information about a 4-dimensional object, the black hole, and stored it on a 3-dimensional object, the surface of the black hole. And when I say 4-dimensional, I am of course talking about 3 dimensions of space plus 1 dimension of time. So it's not 4-dimensional in necessarily the sense you might think. Of course, though, we have to accept that the person who fell into the black hole doesn't experience getting stuck on the event horizon. They just pass through and experience whatever they experience on the inside of a black hole, about which we have no knowledge. And in general relativity, there are no privileged observers, so we can't say this is any less true than the person who saw their friend get stuck on the outside. Does this mean that there are 2 copies of the information? One stuck on the surface and carried away by the Hawking radiation, and one lost forever inside the black hole? Maybe. There are various people who proved that you can't have access to both copies at the same time. So does it really matter if there are 2, if you can only access one of them? What do we really mean by conservation of information? This is the idea of black hole complementarity. You can't access both copies of the information at once. The word complementarity comes from quantum mechanics, where we've got quite used to saying things like the position and the momentum of the particle can't be known at the same time. We're happy with the idea that certain aspects of a system are simultaneously unknowable. So the idea of black hole complementarity is that you can't know the interior and the exterior of a black hole simultaneously. You have to choose one or the other. Let's think of the example of the friend who gets stuck on the horizon. The information about her will eventually be carried away in thermal Hawking radiation. And you could go around collecting that information and then dive in to the black hole afterwards to try and catch up with her, and then you'd have both copies. But she'd hit the singularity long before you'd managed to go around gathering up all the thermal information. And vice versa, if you try and go after her and you hit the singularity with her, then you won't be able to go around gathering up all the thermal bits of Hawking radiation. So there is no way to directly access 2 copies of the information at the same time. Does that mean information is conserved or not? It's not an easy question to answer because we have to think about what we mean by conservation. Okay. So we've come to this idea that all the information on the inside of a black hole can be described by its surface. Let's pick this idea up and roll with it. Or more accurately, let's turn to Juan Maldacena, an Argentinian physicist who has already picked that up and rolled with it, which is a relief because it was probably really hard and I don't want to have to do it. He showed that, and what I'm about to say is a bit of a mouthful, but we'll unpack it afterwards. He showed that a gravitational theory in 4 + 1 dimensional anti-de Sitter spacetime can be described as a non-gravitational 3 + 1 dimensional conformal field theory along the boundary. That was a mouthful, and we're going to go into more detail. Okay, so I'm not keeping up with my PowerPoint, I apologize for that. Anti-de Sitter space is a 4-dimensional Pringle. What does that sentence mean? Well, up to 3 dimensions, we're quite happy with the idea of adding a dimension. A circle is a 2-dimensional dot, and a sphere is a 3-dimensional circle. We sort of intuitively understand this idea that you can go up in dimensions. And we're also quite good at picturing spheres, possibly because we interact with so many of them. A sphere is positively curved space, and a 4-dimensional sphere would be called de Sitter space. A Pringle is negatively curved, and a 4-dimensional Pringle would be called anti-de Sitter space. I can't really tell you exactly what a 4-dimensional Pringle looks like, but if you took a Pringle and squashed it flat, you get a geometry a bit like this. You may have seen, this is the work of M.C. Escher, who did a lot of wood carvings and played around with tessellation and interesting geometrical properties. And this is what would happen if you mapped a Pringle onto a flat surface. you have this tessellating property, but all of the angels, the white shapes, are actually the same size on the Pringle surface, and all of the devils are the same size on the Pringle surface, even though in this transformation to flat surface, they're different sizes. I see there's a question.
Yes, well spotted. How can the surface of a black hole be big enough to hold all the information that has been absorbed by it?
That's sort of the crux of the whole issue. How is the surface of a black hole big enough? I think that's just a reframing of the issue. There's not really a good and intuitive answer here. The answer is just that information lives on surfaces, and somehow all the information fits on the surface. It's like a hologram. That's why we call this the holographic principle. A hologram is something that's 2D, and when you shine light through it, you get a 3D object that jumps out. So somehow a black hole, or possibly space-time itself, works in the same way, to squidge up information until it's compact enough that it can describe a volume with an area.
That is seriously cool.
Yeah, it's very confusing. It's not at all an intuitive concept. I think the name holographic principle is nice because it refers back to this idea of a hologram, which is a familiar representation of changing between dimensions, where you can store information about 3 dimensions in only 2. So you know it can be done. It's just a way of finding the right coding, so you can store the information in the right way. And nature just does this automatically. Okay, so returning to anti-de Sitter space, we've got a Pringle, and then, well, it's a 4-dimensional Pringle, and then we're going to stack them up. And along the stacking axis, we've got time. So it's a 4-dimensional Pringle plus a dimension of time in the stacks. I don't know if I've got another picture here. So you make a cylinder out of these stacked Pringles, but it's the kind of cylinder that when you slice through it, you get a 4-dimensional Pringle instead of a circle. This is one of those things that our brains just aren't equipped for. And at some point you have to look at the picture and think, fine, if I have to accept this, I will. Which is a lot of physics, is just saying that. So we take this cylinder that we've constructed in a fairly tortuous way. And it turns out that if you look at the boundary of that space, so the circumference of the cylinder, what you get is flat Minkowski space. Minkowski just means flat, in one fewer dimension, so 3 dimensions plus 1. And that has a conformal field theory living on it. So what a conformal field theory is a particularly well-behaved kind of quantum field theory. What this picture is saying is that we have, on the inside, a 5-dimensional space-time that has gravity in it. And the space-time on the outside is a 4-dimensional space-time with no gravity. And we can create a dictionary to go between those two things. If we start out with a flat space-time with no gravity, we can apply a certain set of mappings, like road directions, if you will, to take us to this 5-dimensional gravitational theory. And vice versa, if we have a 5-dimensional gravitational theory, we can reverse those directions to get to a 4-dimensional quantum field theory. So that's the idea behind what's called ADS-CFT correspondence, where ADS stands for anti-de Sitter and CFT stands for conformal field theory. It's the idea that in certain circumstances, gravitational theories and quantum field theories are actually the same, but it's only in very specific circumstances. Unfortunately, we don't live in a 5-dimensional anti-de Sitter spacetime. As far as we can tell, we live in a 4-dimensional flat spacetime. So we can't quite apply this theory to our universe yet. But this first formal correspondence theory is very thrilling. it's also quite useful because it means that we can study theories in different contexts. We can add gravity to a theory or take it away, depending on what might make it easier to study. If we could find a further correspondence, possibly between our space-time and some kind of two-dimensional quantum field theory, then we would be a step closer towards finding a theory of quantum gravity, and that's a major aim for researchers. So, why does it work for black holes if we live in the wrong kind of universe? Well, ADS-CFT isn't the only holographic principle. We don't have a holographic principle between our space-time and any other space-time, but that doesn't mean one doesn't exist. We just haven't managed to find it. And I did also slightly cheat in my explanation, but in my defense, it's because this only works for a specific kind of string theory, and half an hour is not enough time to explain string theory. And also, I don't know much about string theory. So we all have our fingers crossed for this specific kind of string theory to work, because otherwise we have to go back to the drawing board on the black hole thing, and we'll be left with this paradox that information gets thrown into a black hole and then somehow disappears. But right now, it's a good suggestion, but we don't know if it's the right one. One final thing I'd like to mention is that when I was asked to do this talk, I was asked about the connection between entanglement entropy and the ADS-CFT principle. Now, you might have noticed that I haven't mentioned entanglement at all during this talk. And that's largely because it's not a key player, but there is an important connection, and I'm going to mention it right here at the end. You recall that I said that black holes had an entropy and it was stored on the surface of the event horizon. Well, you can define entropy using entanglement too. Basically, it's a measure of the amount of entanglement between a multi-particle quantum system. And if you define the entanglement entropy of the event horizon of a black hole, it turns out to be the same as the entropy that Bekenstein defined all those years ago. So clearly there is some fundamental connection between entanglement and the way that black holes store information. But there isn't much on it yet, so maybe this is an area that researchers have yet to dive into. So, what do you think? Did David's Hawking radiation bring down Goliath's mighty black holes? It certainly refined our understanding of both of them. Thank you very much.
And thank you very much. That was fascinating and very well explained. Thank you. We have a little tradition where people use the hand thing, which you'll see happening on the participants in a sort of virtual clapping, which always amuses me very much. That was very good. Are you ready to stay around in case anybody wants to join in a Q&A?
Yes, of course.
Okay. So if you'd like to join in the Q&A, if you raise your hand and keep it raised, then I will promote you to panelists and you can join us. Okay, and I'll do that one by one. All right, any more? Yes, Anna. If I promote you by accident, that's because I'm rubbish at doing this kind of thing.
Just say, I'm just going to turn off the live stream now.
Okay, thank you, James. Yes, that's what you do as well.